up, which is a screen space projected mesh LOD system, which is different than like a Quadri or something like that, in that it's a mesh that is projected in screen space. So we take a look at the wireframe. We have a consistent mesh density at all view distances. So if I move out, the mesh density doesn't change. And that's because our mesh is being generated in screen space, or no, it's being transformed into screen space and then projected onto the whatever surface we want. So that gives us a high resolution at all view angles and distances with no like visible transitions between different LODs. But it does come with some issues, like you can see, slow it down a bit, you can kind of see it flicker a bit. It seems like you can reduce this by using a higher res mesh. Um, so I may do that, but if I just go back into wireframe, you can kind of see what it looks like. And it's because it's in screen space, it's moving with the camera instead. Like uh, our mesh is actually in front of the camera and then being projected onto something. In this case, we're projecting it onto a virtual plane. But today, I want to go and take the same logic and work on projecting it onto a sphere. So we have this right here. I believe this is our view space. So let's. This is the second material, so we can go ahead and unattach our water stuff from this. We're just going to plug straight in this, and then we're going to plug this in. There we go. Okay, now we have our screen space mesh. Let's also content drawer, ultra high res, select this. Okay, now we have our screen space mesh. The mesh is following our camera, right? And we don't need this normal, we don't need this base color. Now we just have a plane that's stuck to the camera. So this is the world position we're going to start from right here. And we can get rid of all of this stuff up here, because this is all dealing with projecting it to the plane. And we want to project it to a sphere. So what we want to do, let's just get rid of all of this for now. We'll keep our Gerstner wave stuff in here, but we're not going to use it yet. No inputs to single layer water. Okay, we don't need to be single layer water right now. We're just going to be default lit. I'm not sure why it's flickering, but we'll leave it as this mesh here. And you can see it's a really high density mesh. We can't even see the subdivisions here. So we're gonna, all right, so we're gonna run this by coworker. Okay, next we are experimenting with a screen space projected mesh LED system. We want to try to wrap it around a sphere intersection. We only we care about the first intersection with given the each vertex's transformed screen space position, we need to cast a ray from the camera through that vertex position and check intersection with a sphere we will define with a center position and a radius. If we then care about the first intersection, either from either inside or outside the sphere, we will then need to calculate the displacement vector to translate the meshes, the current vertex, to the position on the surface of the sphere. If there is no intersection, we will translate the point to the center of the sphere. Okay, stop. Okay, first off, the ray origin will be the position of the vertex, since we need to calculate the displacement. The ray direction can still be the same, though, I think. Okay, so we don't need to output the you don't need to transform the vertex position in the shader in the HLSL. It should be enough to return the displacement so that we can plug it into world position offset. Hello. We're working with screen space meshes now because it's cool and I was interested in it. It gives us a consistent mesh density without having to do like changes to the mesh itself. Yeah, so we're like here's a picture. We basically make a really high density mesh and stick it in front of the camera with some math. And then through each vertex of the mesh, we cast a ray. And in the example we've got, we're intersecting with a plane, but I'm working on making it intersect with a sphere. And that gives us like a consistent mesh density at all viewing angles and distances. So like our mesh density isn't changing even though we're getting really, really far away. And that's because we're projecting it in screen space. It has some drawbacks, but it's also pretty cool. So I wanted to do some experiments with it. Nice. Did you do good, dude? Integration with world position offset. All right, let's give this a shot. It's actually not heavy at all for the CPU because it's just a single static mesh. We're not doing like we're not doing any like real-time adjustment of the density of the mesh or anything like that. You just have a single static mesh that's high density and then you transform it in a fragment shader. So it actually is pretty efficient. Camera position, camera vector, sphere center, sphere radius, or just um, so like you're not generating any mesh or anything at runtime. You just have a static mesh that's basically attached to the camera in a way where it always is in view of the camera. And then you take that mesh and you transform each vertices to the position to like basically shrink wrap it around stuff. Um, Position vector center radius is what we'll call our inputs here. And then back over here, we just have position Camera position. Okay, we can do it this way too. Center and radius. And then we just go back here and change this from vector to... Yeah, I followed a guide to get the initial transformation set up. It was this guy Ghislaine Girodo's screen space grid generation method, and he goes through the material setup, which because like okay, so I'll show you for example, if I apply a different material to this mesh, the mesh is doing all the heavy lifting. I mean, the material is doing all the heavy lifting. So if I just put like this on it, right, and unselect it, go to our directional light, the mesh is just here in our scene. Like it's not actually moving with the camera or anything. The material is just a high res mesh I made in Blender, right? The material does the initial transformation to lock it to the camera. So if I were to then take this guy and put screen space mesh back on it, then unselect it, now it's locked to the camera. And it's just being projected onto like a basic, my basic Gerstner wave um, formula. But like the main thing is like the mesh is still ostensibly where it was in the screen. The material is what's doing the transformation to move everything, move all the points. All right, so next you're looking at this vertex position, camera position, sphere center, sphere radius. We don't need these, I don't think. Tab this, take, we don't need this. We don't need this. We just need this and this. So with this, it's within this version, it's being mapped to a virtual plane, and we're trying to map it to a virtual sphere. That's kind of what I'm trying to do right now. So paste this. Um, this is so our position is our transformed screen space position right here, and then our camera position is the camera position. And then these are manually defined, so we were just finding a sphere with a center at 0, 0, 0 and a radius of 200. And then this should be returning an offset. Okay. It's not quite there, but it is sort of doing a thing. Huh. Yeah, so it's not quite right. Let's see what it looks like in the scene. And let's make the radius a little bit bigger. This is definitely not it yet, but Well, it works as soon as we get close enough to it, sort of. I'm not sure what this is. Probably our intersection stuff is wrong. We're not doing any normal changes either, which is part of the jankiness here. Yeah, you can. So you actually have to in the HLSL in the material editor because it's technically encapsulated in a function. So you can't make other functions without wrapping. Like if you want to do function libraries in the custom node, you have to format them like this. You make a struct, you put all your functions and stuff in that struct, and then you can invoke them from outside of it and return your result and things like that. All right, let's take a look at the math here. So vertex position, ray origin is the vertex position. Yep. Camera position, ray direction, normalized vertex position minus camera position. Um, I guess we can go in the material and mess with it. Do we perhaps need to invert our ray direction? Nope, that's not it. Intersection point. It would almost, hang on. Okay, so let's use a little bit lower density mesh. Um, let's do this guy. Yeah, so there's something going on. Because, like, this is what we want right here, right? Pretty much. Or not exactly, but it's like right here, it's just about correct. Here, it's not correct. The only place I'm using the camera position. I can't even use that. Okay, interesting. Instead of returning the displacement, I just return the world position. Oh god. Let's save it and look at it out in the outside of this editor. Alright, and this looks pretty bad, but it's probably just because we're using the lower resolution rectangle. Ultra. There's rectangle. We may need to go even like one subdivision further, maybe. But it does sort of work. So what if I get close to the surface? So you notice how the grid isn't shaped like a sphere, but it's still just like shaped like a grid? That's because of like it being in screen space and then projected onto the sphere. And that's also why we're getting these little jaggies on the edge here too. But it's a neat concept. I'm not sure if I'll be able to use it or not, but it's cool. It doesn't have appropriate normals either. Uh, okay, and how can I calculate some basic sphere normals? Minus, okay, perfect. Easy, easy, easy. So we can do that pretty easily. So we actually take, this is our displacement, this is our actual world position. So we can take this and subtract the center and normalize and plug this into normal. I wish I knew I was flickering like this in the editor. So so the fundamental difference between this and like an actual mesh sphere. So there's a bunch of drawbacks with this. You can't have collision because it's all done in like GPU. So no collision. But with water, collision doesn't really matter. But the big difference between this and like a normal sphere is that a normal sphere has a mesh following the topology of a sphere, but this mesh has a topology of, well, actually, we can't really see it very well. Let's do this again. We'll just take out rectangle. We'll grab this lower resolution rectangle. This mesh has a topology of a grid that's always facing the screen, right? And then what I'm doing with all the points that are outside of this, that aren't intersecting the sphere, is I'm just setting them to zero, or not zero, but the center of the sphere. So that's how we're hiding the points of this mesh that would be like covering up the rest of the screen. We just move all those points to the inside of the sphere. And our topology ends up looking like this, and it doesn't change based on the angle, and it doesn't follow like the curve of the sphere because it's just a grid in screen space, so it's always the same. Um, there we go. And there we go. So the one thing that we do need for this to work properly is a really high resolution mesh. in order for it to not get super janky. I mean, it still kind of does, but we could even potentially subdivide this one or once more, maybe. But I went ahead and you can see it gets janky on the inside too because of all the points being grabbed towards the inside. So you'd have to figure out something to do with the inside of the sphere, some way to like turn visibility off. But I added in sphere normals and I fixed the intersection algorithm so that it's actually making a sphere now, which is pretty neat. So then theoretically we could apply like our wave functions to this sphere and have our water LOD without having to generate extra meshes in our like C++ code. We would just have to set the radius that we want our water to appear at. It does have this issue of getting choppy edges. I wonder if Blender will crash if I subdivide this one more time. Alright, are we gonna crash? Didn't seem to crash. Mega Ultra High Resurrect. Alright, here's one more subdivision. Might take a while for this to import. And hopefully it doesn't crash Unreal either. Just let it cook. I hope I saved this. I think I did though. That may be more than it can handle. We'll see. I'll give it at least a couple minutes. Sure. Ugh. How come Blender can handle this but Unreal can't? don't know if it's gonna do it. Maybe I'll play a game of Magic and come back to it. Let it continue spinning. I can go ahead and close this down. I don't think we're gonna get any higher resolution than what we just exported. Free up some resources. Blue or red, huh? Blue or red? F equals x to the third, 2x to the square, 2x squared minus ax plus 2a. Find it greater than 0 when x1 plus x2 plus x3 equals 8. Yeah, that's pretty difficult to do on just a test. Like I would probably have to look up stuff to figure that out. We got instant, land, and enchantment. We need this creature to die, and then we would have it. Did we hit any lands? We did. Sure. Yep, we're fine with that. We wanted him to die anyway. Let's snag a breeding pool. Let's go ahead and just pop off an Atraxa. Oh, Omniscience on the top of the deck. That's amazing. Yeah, we win now. Enchantment, Thirst, Sorcery, Land. Fae of Wishes. We win. Nice. Yeah, see, like I don't generally keep the way to solve math problems in my head. I'm just not afraid to go figure it out. Hey, it imported. Hell yeah. So Mega Ultra. Let's move this into here. Okay, and then let's grab this, select this, and set it as our preview and see how that deals with the jaggy edges. Yeah, see, now we have smoother edges, but I think it is slowing us down a little bit. So we come out here, we get this, and we switch it to Mega Ultra. And it actually looks pretty good, but it is slowing me down. Tools, audit. Where's my Where's my FPS? Um, Hang on. How can I view FPS in UE5? It's like maybe it was like F1? No, that's not it. Stat FPS. Tilde. Okay, perfect. Yeah. Yeah. It chugs a little bit. I am curious, so hang on. Screen space mesh. Oh, yeah. It's chugging. So that this might be beyond what we can actually support. It does get rid of the flickering though. It's high enough resolution to where we have like a polygon per pixel probably, and it gets rid of the aliasing. It's just not super viable. It is smooth, however. Like it looks pretty reasonable next to like a regular mesh. Hmm, pretty interesting. So let's see. Next up, I want to make it bigger. We also, okay, so I'm thinking about this, right? So we need two cases. When the camera's inside, or when the starting point of the, okay, yeah. So I'm just thinking. Um, I got to think about how to handle being inside of it, right? Because right now what we're doing is we're taking a point that was like right here. So like a point that was here is getting transformed to the surface of the sphere, but a point that was here is getting transformed to here, which works when you're outside the sphere. But if I was inside the sphere, if this point was inside the sphere, then its projected location would be here. And this would not be visible. So what do we do? Well, wait, no. If we're inside the sphere, then the point should always be projected to the sphere. Hmm. Thinking about this. I guess I'm probably when I am all the way inside the sphere, it's not a problem. It's only a problem when we're like partially breaking the surface of it. Because like right here, it really chugs. Right here, we have all of these guys out here that are not intersected that are being projected to the inside. So I need a better solution. Need a better solution for handling those verts. Also, we need to tone this down a bit because it chokes my computer. Hey, buddy. Ugh. Right, move your paw. You're on my mouse cable. So let me see how I did it in the other one. Virtual plane coordinates. We have an if here. Oh, no, not this. No, don't save the changes. It's here. So here, we took this in. Okay. thinking. No bad ideas. Oh yeah, so that is what I want, but it's kind of a challenge. Sorry about it. Hang on. Let me let you up, okay? You don't need to. Oh, she unplugged me. All right. Hang on, hang on, hang on, hang on. I'm gonna pick you up. Oh yeah, yeah, yeah. All right. Um. All right. She unplugged my computer, so just a second. There we go. So in the other one, we did it by multiplying by a very, very large number. So I'm just gonna give that a shot. Yeah, that's what I was kind of afraid of. I'm curious what it's gonna look like, but well, hang on. Hold on, hold on, hold on. Maybe it does work. I don't know why it flickers like this. It's just so far away, it's like outside the clip plane. Interesting. Very interesting. So now if I stick my camera inside of it, it's just normal. Pretty cool. But if I go into wireframe, that's ridiculous. That's pretty neat. Um, hmm. So that does work. And we can get rid of, so what we'll do is instead of this, um, we have like all these else. I like making my code as simple as possible. We don't actually need these else's. We just set this to be our initial value. And since there's only one case that sets it to true here, we can just get rid of both these else statements. It's functionally equivalent. That is so wild. Look at that. It's fucking crazy. Yeah, there's no such thing as a stupid question, man. Like that's what I was trying to do. I just didn't know how to do it. My initial instinct was to push all the because like now you can really see what I'm talking about with this being like a mesh in front of the camera rather than being a mesh that is like in world space, because we obviously have all the points projected out to infinity here, or not infinity, but very far. And basically, what we have is like, if I was going to draw this from like a profile view, it would look kind of like this. So all the points here are projected like a super far distance away, so they're outside of the view frustum. And then all the points here are projected onto the surface of the sphere. And so when you're in wireframe, you can still see all the points. And because the points are projected along the camera vector, the space between them, like from your perspective, doesn't change. And the only caveat is you basically have to, when working with your formulas that take world space into account, you have to basically use this value as your world space instead of the actual world position, because you're translating them. And then this final function here is what translates your position from where that plane actually is to where all of its vertices are being displaced to. All right, so this will be projected, named reroute, projected vertex normal. So we replace absolute world position and vertex normal whenever we need those things with these. Let's take a look at the normal output here. I don't know why it flickers like that in the editor though. But yeah, we've got so we've got our sphere normals or our vertex normal set up correctly, it would appear. Um, it's pretty neat. And then you just change the size of the mesh by changing the radius here. So if you wanted like a planet-sized sphere, we have to save it. Oh boy. I think we're hitting precision problems though. At large scales, it would seem. Yeah, so it might still not be super viable. Take it down in order of magnitude. Turn off the exponential fog. Which actually makes sense, because if we're projecting our stuff out really far, so let's try, hang on, I have an idea. If I increase this, yeah, so it, excuse me, so it probably is still not going to be viable because of precision issues, is what it seems like. Huh. So yeah, I'm not sure this is going to be usable. At least not at the scales we want it to be usable at. Run into floating point problems. So this would be centimeters. This would be only 10 kilometers. That's not enough. Another thing that we could do, hang on. What if what if, okay, so what if we change this from opaque to masked, right? And then we add an output here, intersect mask. Okay. And then out int intersect mask intersect mask. Uh-huh. And then we just say intersect mask equals 1. Intersect mask equals 0. Like this. And then that successfully hides the background, at least. And then we don't have to worry about this nonsense here at all. It's it's probably not going to work. And it's not the formula. The formula is correct. The problem is like the actual floating point math that's occurring. Although our ray intersect formula works in our atmosphere shader, and that one is really big. But that one is also volumetric and doesn't need to be incredibly precise. Hmm. Yeah, see, like there's something going on here. I'm definitely gonna play with it more. Why is it doing that? I'm like, what? Yeah, maybe there is something wrong with the formula because that doesn't seem right to me. And this doesn't seem right either. Does not appear to matter. Oh, I know why it's fucking up in here, actually. It's because the bounds extension isn't set. Um, aha. Okay, hang on. How big can I make this? So it works really good at smaller scales. Like it doesn't seem to have a problem, sort of. This isn't right. But oh, I know why. So we got to do this. Maybe. Maybe, maybe not. It might not be the same. Hmm. No, I don't think it's having an effect. It's not a two-sided material in the first place because we're like smooshing it. Uh, you probably need like some form of LOD to handle that, like another sphere to sub in once we pass like maybe here or something like that. Let's see. Let's bring coworker in here. Okay, so I have the screen projected mesh set to wrap around a sphere. I ended up making it masked and outputting binary mask based on if an intersection occurred and use that to set opacity. Seems to work okay at small scales, but it breaks down when I set the radius to large scales. For instance, at 10 km, there are a lot of there is a lot of jitter and artifacts. A lot of jitter and artifacts. Know that I have used sphere intersection in my atmosphere shader at very large scales though, so I'm not sure why it's breaking down here. Um, Here's the current sphere intersect code. Interesting. So he's basically we can just integrate a baseline scale into the formula. Let's try it. Let's try it. Uh, let's see what happens. No, I'm afraid not. um, hmm. Interesting. So what did they try to do? Scale. And it may have to do with this stuff. Like the most likely answer is that it has to do with the this here. It works up close, sort of, but not from far. Um, I think that maybe the sphere intersection is not actually the problem. The function to transform the high density rectangle to screen space is relying on several transform vector nodes, and I'm wondering if maybe that is what is breaking down at large distances. I mean, you could conceivably physically lock the plane, like instead of transforming it in material space, we could physically set up a custom camera that has the plane in the right position in front of it. Uh, so like, let's try that. We're gonna create a new blueprint. What if instead of relying on the material to do the translation between the high density meshes base location and the screen space, we create a custom camera blueprint that has the high density mesh box in front of the camera, just at just past the near culling point. Then we would have to modify the scale of the mesh in the material, but not the location of all its, but not its location. So we could cut most of the transform to screen space stuff. A high density mesh component of the camera actor, custom camera actor. Create a new blueprint actor. Okay, that's what I was wondering. Blueprint actor. Um, BP screen space mesh camera. Add static mesh. Green space mesh. Oops. So I suspect what's going on is that these transform to vectors are probably not designed to work at really large distances because usually you would need them that way. And so our initial, like, this is what's picking up our mesh and basically putting it in front of our camera. So if I do that in, like, real space, then we don't have to do any of those calculations, or we shouldn't. Ultra high res rects. Okay, perfect. Add a camera. Nope. 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 We fucked it now. All right, and 90. Okay, great. Camera's at 0. I think it says that it's generally 10 units is the near cull, so that's gonna be 10 scale 0.5. All right, and then 11 so that we push it just past the near clip. And then we'll have to figure out, given the camera and this, how to properly scale it. And we don't even have to do that in the material. Alright, later, dude. So, and we can parent this to the camera. Great. Reset. Alright, so let's grab coworker. Okay, so I have created our base blueprint. It contains a static mesh with our high density mesh and a camera parented pair facing the camera and a camera. The mesh is facing the camera at 11 units in front camera. Now we need to figure out how to properly scale the mesh in instruction script such that it occupies camera FOV. Um, with the mesh parent, with the mesh as child of the camera, I don't think we should need to update its position in tick. We just need to figure out how to properly scale the mesh in the construction script or mesh so that stick this in our scene so that we can view it. We're gonna go ahead and get rid of this guy for now. We're gonna add a screen space mesh camera. Alright, and we can actually just, I mean, realistically, no, 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 no. something like that, and then we get this, we go wireframe, we go lit, pilot, seems okay. Alright, so now we can eject. Okay, so now we have our special camera here. Let's go make a third screen space. Do screen space, mesh sphere, simple. Simple. Alright, so we go in here. We don't need any of this anymore. This is all used to convert it. We just directly use the world position. Save it. And let's take this. Green space mesh simple. Let's go in here also and change our scale for a moment and make sure that it works the way that we think it does. We'll make this small. We wouldn't expect this to work properly. And now we can take this camera as our placeholder. Let's do the shapes, sphere, 0, 0, 190, 190, 190. Okay, I see. This is way off. Okay, go over to here. Pretty interesting. Let's turn off our height fog and sky atmosphere and everything. Alright, so now let's make this really big. It sort of works, but when we get really far away, it still breaks down. So let's see if it has the same problems when we make it really big. And yeah, it does. Unfortunate. Yeah, I don't think we're going to be able to use it. Hmm. Is there such a thing as double? Is there such a thing as double ratio? So, how would you simulate double precision and only using multiple floats? What is the precision of scalar values in UE5 material? Material expression. Duh. Oh. Interesting. So we could do it. We just have to adapt all the math to operate on float twos. So like our float threes become float sixes. Another idea. What happens if we increase the scale of this thing? Hmm. At this scale, it works just fine, though, until you get really far away. Screen space, projected mesh grid breaks down at a large scale. Trying to implement. Mm-hmm. Well, I might play with this a bit more, but I'm gonna take a break for now. What you're here, I'll show you, dude. It's kind of cool. What you're looking at is a sphere, but it's not actually a sphere. It's a screen space projected grid. So what we basically have is a rectangle. We'll just put this on it and go to it. Oops. I forgot that it's got huge bounds. Hang on. Um, Go here. There we go. All right, we're back. So where's my grid? There we go. Way over there. All right, so here we go. So we got is basically like, yeah, it's all good. What we got is basically like a really high density just quad or just rectangle here. So if we go down, we see that this is like a really highly subdivided mesh, right? So what we can do with that is kind of cool is through this material. Let's do flat first. So what this is going to do is it's going to basically take this mesh and stick it to the camera with a transformation so that it overlaps the viewport perfectly. And then it projects it to match a different mesh. So if I double click this, so what we got now, it's that same mesh, but it's projected onto the camera. And if we go to lit, I've got just my basic like Gerstner wave ocean shader that I've been working on with it, which I did kind of figure out at least a basic crest mask here. But so what's cool about this is because the mesh is generated in screen space, we basically have infinite LOD. Like we don't have to generate mesh at different LOD levels or anything like that. If I go to wireframe, you'll see what I mean. As I get further away, our mesh density stays consistent. And that's because the mesh is attached to the camera itself. Um, and then it's projected in camera space. So like, I drew a picture of it somewhere. So like here's an example. Like we got our camera here. We have our mesh put in front of the camera so that it occupies the entire view space. And then we have some object that we want to draw with this mesh. And we do that by projecting along the camera ray every point of this mesh until we hit the object in like virtual space that we want to represent. And then we calculate a transformation from that vertex to that point. Um, so what you're looking at here is using the virtual plane coordinates to do that. We get this, which gives us basically an infinite ocean plane with infinite resolution, right? Or not infinite resolution, but we will always have the same basically verts per pixel at all levels. So it doesn't matter how far away we are. We have the same amount of geometry in a given portion of the screen at any given time. Oop, there we go. So we don't have to generate like we don't have to generate meshes, we don't have to do like quad tree stuff. It's literally just because the mesh is in screen space, it's always the same resolution regardless of how close or far away we are from the surface, right? Performance is actually really good because all it is a single static mesh attached to the camera, or not in. It's virtually attached to the camera by the material. Like the mesh itself is actually still over here, but we're calculating what we need to do to basically attach this to the camera in the material itself. So it's actually this portion here converts the material from, or converts all the verts from wherever they are to be like basically overlapping the camera. And then this part here is projecting those verts from that transformation onto a virtual plane, which this is just copied out of virtual plane coordinates. So inside this function, it has basically the logic that we're looking at. We just don't need the normals or anything. Um, and this is all, so like this one is all from this video here, a screen space grid generation method in Unreal Engine by this Ghislaine Girardeau guy that I found. So I followed this to do that. So what you were looking at when you first hopped in and were wondering what it actually was is I created a different version of this. And this, instead of using a plane projection, an infinite virtual plane projection, this is using a sphere intersection algorithm to basically place the grid. So if I go into wireframe, you can see that our mesh here doesn't follow the topology. Well, I mean, you can't because it's too dense. But if I was to do, let's do this. We'll go down in resolution a bit. You can see that the mesh is not actually following the topology of the sphere that it's rendering. But rather, it's consistent in screen space. And this is really useful for something like ocean waves or things like that, where you want to be able to have like a consistent LOD. It has some limitations. You can't use collision with it. No, you can't have collision with it. So you wouldn't want to use because it's all based on world position offset. So you wouldn't want to use this for something like terrain because you couldn't walk on it. But for something like water, it's actually not a huge deal because you generally aren't going to have collision on the surface of your water anyway because you can go inside of it, and you would rather do something like buoyancy based on like where you're at relative to sea level, right? Um, but you can see like we have consistent geometry no matter how close or far we are away. The problem I'm running into is that it's breaking down, at least for this one, which I don't know why. So like if I do this one right, this is using sphere intersection, and I go far away from it, it starts breaking down, which is understandable. But what I don't understand is why when I use the original one that's using a virtual plane, why I can get really far away from it on the like x-axis without it breaking down then. Because I would think if I was running into like precision issues that I would hit the same precision issues here, but it just works. So it's very confusing. And I'm not sure why, but right now as it stands, I'm probably not going to be able to use it because of the precision issues when I do it with the sphere calculation. And I'm going to, but it's a really intriguing concept. I think um, it's got, it's definitely got some interesting applications. I'm just not sure I'm just not sure how to fix it so that it works with what I have. You know what I'm saying? Like, because wrapping it around a sphere is different. The other problem is I do this. We'll go back to the origin. All right, so we go in the material and I make it much bigger than this. We start running into big issues, which you should be able to see. So, like, for it to get big enough for me to use it, I have to overcome this issue, and I don't know how. Because I'm pretty sure it's like floating point precision issues. I have a few ideas. Like, we could switch it to double precision by using float 2 for every float value. So, like, all our float 3s become float 6s, all our float 2s become float 4s, all our floats become float 2s. And you could represent like two halves of the double in each piece of the float and then reconstruct it. But I'm not sure that that would even matter because the material itself is using float 32s. So, like, it's a lot of work to do that. The other option is you could make really small planets and then have people just like scale the character size down, I guess. But you would probably run into some issues with that. So I'm like, it's a cool concept, but I'm not really sure if I'm going to be able to harness it properly to make use of it. So like at 10E5, it seems like this is about as big. At least this is the last order of magnitude before I stop being able to like get precision up close to it. And this is only, let's see, centimeters, kilometers. So this is only a kilometer in radius, which is definitely not big enough to use it. But I feel like I'm missing something because if it was purely impossible, then I would expect this one to fail at some point when I get far enough away from the origin, and I'm like way further away here at this point than I was away from the sphere when it was breaking down, but this is still working. So it's not hopeless. There's something I'm missing. Um, there's definitely something I'm missing here that might make it work properly, and I don't know how to do it. I'm kind of curious what would happen if I converted it to nanite as well. But it is cool. So yeah, I was at least able to make a sphere with it. I just can't figure out how to get this to be precise at like the scales I need it to be. And what this is basically doing, if I open it back up, I basically have a ray sphere intersection, and this is outputting two things. It's outputting a world position of the intersection starting from the world position of, or the translated screen space world position of the vertex. So this would be like each vertex in that plane once it's been moved in front of the camera. We start from that position. We cast a ray from the camera position through that position and do a sphere intersection. And then in that sphere intersection, I do an intersect mask. We default it to 0, but if we have a hit, we set it to 1. And then we output that intersect mask into a masked opacity, so we can hide basically the any vertex that did not intersect the sphere will have a 0 opacity, right? And we can actually, if I do this and go out here, you can see the whole thing, right? So if I go wireframe, you can't tell. You can't tell where the sphere is because all the geometry is completely consistent. It's just hang on. You can't tell where the sphere is because all the geometry is consistent. So you have to plug this back in to be able to have it actually match up and like hide it, right? So that you can see the rest of the scene. Um, but yeah, that's it. But depending on what your end game is for the game or project for the scale, yes, exactly. You could. This would be really good for like modeling things that need like a high resolution, but you don't need to interact with. So like liquid flowing over a surface or something like that, you could probably use this to do a really good version of that. Also, if you just wanted a completely flat ocean, it would be great for that because you could just run this and you've got it, right? Like, um, if you could run this and also figure out like some depth equations to integrate depth so that you get like shorelines and stuff, like if you weren't trying to fly from space to the planet, this would be a great ocean. Except for the fact that it doesn't work underneath it, but like you could fix this. Like I just haven't yet. Um, but yeah, if all you wanted was an infinite ocean plane that had a high resolution and like consistent appearance from different view ranges, like it will already do that just fine. But yeah, so I've been kind of monkeying about with this method for the past few days, past couple days. But yeah, I'm about to grab some lunch and take a break. So later, dude.